Okay, so we talked about compact spaces last time, and we defined what it is. It's a space such that every open covering contains a finite subcover, which I tried to explain last time seems a little not that intuitive. There's an alternative definition, which is for closed sets, like a compact space. A space is compact if and only if you have the finite intersection property, which we'll get to later. That's a condition about closed sets, but it's as equally non-intuitive. So the things that were more intuitive, things like Bolzano-Weierstrass, or that turned out to be not quite right, but we'll get to those later. And so let's do the usual thing. Let's go through the various topics and see what compactness interplays with those topics. So subspaces. If you have a subspace of X, then that subspace is compact if and only if every covering of Y by sets open in X contains a finite subcollection covering Y. And so you might look at that and say, what? How is it any different from the definition of compactness? Of course, it's compact means that every covering of Y by sets open in Y has a finite covering. Now we've just put the subspace in some bigger space X and say it doesn't matter whether it's open in the subspace topology or it's open in the main topology, it's the same, it means the same thing. And basically, you just think about what it means to be open in the subspace topology, right? Going in one direction, so say you've got a covering, so let's say Y is compact, and say we have a covering of sets open in X. Then, if you intersect each of those open sets with Y, you get a covering of sets open in Y. And now you use the fact that Y is compact means that you've got then a finite subcollection of these guys that cover Y. Okay. Well, then you go back to just your A's. They're actually bigger, right? Because we now ignore the intersection with Y. So the initial A's, that finite collection will cover Y. So, and then going in the other direction, it's exactly the same proof, really. So now you want to show that, now we say that Y has this property that every covering of Y by sets open in X contains a finite subcollection covering Y. So now we want to show that Y is compact. Okay, well, you take a covering of Y by sets open in Y. The fact that they're open in Y means that they're the intersection of some set open in X intersected with Y. Right? But now you use the fact that there's now a finite subcollection of those A alphas which cover Y. And then you go back to these, that means this guy is also finite subcollection of these cover Y, and so therefore Y is compact. So it's really, we can go back and forth between the sets open in X and open in Y just by intersecting with Y. It doesn't really cause any problem. So that lemma was just a useful thing, useful technicality that we can use to prove the main result is that every closed subspace of a compact space is compact. Oh, hang on. Got to get my logic correct. No, we don't need that. We don't need 26.1 for 26.2. Okay. We want to show every closed subspace of a compact space is compact. Okay. Well, let's say that Y is a subspace of X, and let's. I guess we do need 26.1 because it doesn't matter whether we're talking about open sets in X or open sets in Y. So I guess it does kind of matter. Okay, so of course the way that you prove anything about compactness is assume you have an open covering and then prove that there's a finite subcovering. So we start off with our open covering of Y, and now just add to that collection the single open set X minus Y. If Y is closed, then X minus Y is open. And what can you tell me about this new collection of open sets? So this covers Y. This covers the parts of X that aren't in Y. So together, it's an open cover of X. But now we use the fact that X is compact, and we say, okay, there's a finite subcover of X, and we look at that finite subcover. If X minus Y is in there, right? It has to be in there. Well, we just throw that out, and we're left with a finite subcover of Y. So that's pretty neat. So all these proofs kind of look the same, you know, and you'll see after a while why that. You might not see why that definition is intuitive, but you'll definitely see why that definition is useful, because it's much easier than fiddling around with sequences and all that. Okay. Here's another useful lemma. If Y is a compact subspace of a Hausdorff space and X naught is not in Y, then there exists disjoint open sets U and V containing X naught and Y respectively. So for compact subspaces of Hausdorff spaces, you can do a little better than you can do a little better in the separation. So typically you can't just separate everything. Hausdorff, all you're doing, remember, is you can separate 2 points. By separate, I mean being able to put disjoint open sets around them. Okay, but you can separate compact subspaces from points that are not in the compact subspace. And again, the finiteness property of compactness comes in, right? Because with open sets, you can't just willy-nilly intersect open sets and end up with an open set, right? You need only a finite number of intersections, right? And so that's where the compactness is. Use it. So here's the picture. So Here is x naught over here, and here is y, some space here, some compact subspace away from x naught. Okay, so since it's a Hausdorff, we can separate the points, we can separate x naught from the points within y. Okay, so for each point y in y, we can come up with an open neighborhood of those, and correspondingly we can end up with disjoint cover of x naught over here. Now, if you look at all the collection of these neighborhoods of y, that's of course an open cover of y. So therefore, there exists a finite subcover. Okay, and so here we go here. And so here is our finite subcover. Now, corresponding to that, there's a finite number of open neighborhoods around x naught. Now, of course, the trouble is, for example, this neighborhood is disjoint from this one, but the other neighborhoods might not be disjoint from it. So what we do is we intersect things. So if we intersect all the neighborhoods around x naught, we end up with an open set because there's only finitely many of them. And then over here, well, if we look at the union of these neighborhoods of our points in our finite cover, that gives an open set. So here we have an open set from unions. Here we get an open set from intersections. And they're disjoint. Because any point that it's in this open set, right, is going to be in all these open neighborhoods here. In particular, one of them is disjoint from something in over here. So this intersection is going to be disjoint from these guys over here. Okay, so that's an example of what we call a separation result. So separation is another useful topological property. And we've already seen examples where levels of separation kind of mean nicer and nicer topological spaces. So like we started off with T1, T2, and then in that example, we had this idea of, regularity, where you could get around any closed set, you can get an open set disjoint from the neighborhood of that point over there. And that lemma is used now for theorem 26.3, which is that every compact subspace of a Hausdorff space is closed. And that follows really directly from the lemma, right? Because every point in Y has a neighborhood disjoint from Y. Well, that's definition of open. Right, so the points not in Y is in an open set, so therefore Y is a closed set. So it follows straight away from that lemma. In the book, you might notice for some reason they put things, I thought it makes more sense to put things like that. Okay. So let's have a look at some examples of compact spaces. So any closed subspace of a closed interval in R is compact. we haven't proved that yet. We'll prove that when we come to looking at compact spaces of the reals. But we know straight away that open or half open intervals are not compact, because that follows straight away from 26.3, right, which says that compact subspace of a Hausdorff space is closed. So anything that is not closed in a Hausdorff space cannot be compact. And of course, R is Hausdorff. Now, let's think about the Hausdorff condition. Why is it necessary for that to make sure it's closed? Well, let's consider R with a finite complement topology. So that is not Hausdorff. The finite complement topology means that the only closed sets are finite sets. What are the compact sets in the finite complement topology?
All the closed sets would be, right?
Yes, all the closed sets would be, because there's only finitely many. You can always. Okay, what about if you have any? Well, let's think about the whole line, the whole real line. Let's say we have a cover of R by open sets. And so that means we've got a collection of sets which are just R minus finite number of points. Well, if we go search through them, we can find a cover of R, just a finite number of them is going to cover all of R. So it turns out that every set in the finite complement topology is compact, just because open sets are so big. What are the compact sets in the countable complement topology? So remember, in the countable complement topology, the closed sets are the countable subsets of R. In this case here, it turns out that the compact sets are the finite subsets of R. And the proof is kind of nice because it's an example of a really useful technique that's good to know. So let's say we have let's say it's a compact infinite set. So let's argue by contradiction. So if it's a compact infinite set, then let AN be an infinite sequence of different elements. Of A, right? So AI doesn't equal AJ if I doesn't equal J. Okay, so we can do that because it's an infinite set. We can just do that. Okay, now let's think of the following. So this is a standard way that you show something is not compact. You show that you have an open cover which can't be finite. And consider the following sets. OI equal to I guess R minus the A J such that J is greater than or equal to I. Okay, these are open sets. We just remove a countable number of points from R. Well, this is an open cover of but it can't have any finite subcover, right? Because what would happen if there was a finite subcover? How do I finish off the argument? So if there's a finite subcover, then there has to exist an O capital N, right? Where N is the largest. And then you're missing out on that tail there. So a really good trick is to construct sets such that C1 covers C2 or the other way around. Such examples always give you really interesting counter examples of things. So it's a handy trick to keep in your mind. Okay. Every compact subspace of a metric space is bounded in that metric and closed. Okay, well, it's obvious it's closed because metric space is a Hausdorff. Why are they bounded? So try and think of an example like this.
The open sets.
So let's say A be a compact subspace in metric space X. So let's choose an A as an element of that. And so what can we do? How can we construct some open sets from that, given a point?
Epsilon balls.
We look at epsilon balls. Well, we don't want to look at actually at epsilon balls. What about balls of distance n? Right? And so then if you look at the union as n of nz plus, this covers A. It's an open cover of A. A is compact, so therefore finite subcover.
And then there's a maximum n.
And it's a bound. So yeah, like I said, this kind of trick where you just kind of construct a sequence, one containing in the other or the other way around, is a really useful trick. Here's a weird question. What What's a matrix space in which not every closed bounded subspace is compact? Can you want to start a guess at that?
Maybe it's the box topology.
I think that was my guess too, because obviously it has to be something infinite dimensional,
Yeah.
right? And the product topology, we're going to think that the product topology is going to be okay, but the box topology, because if you think about it, you take, I think this is called the Hilbert cube, where you just take the interval 0, 1, and do that, and then put that in the box topology. That can't be compact. Because I think you can just put like an open set just around each component, something like that. I'm sure you can turn that into it. But anyway, that's my guess as well. I didn't go into the details, but I'm pretty sure that can't be compact. Okay. Continuing our tour then of concepts, continuous functions. And this one really, I think, really kind of illustrates how the definition of compactness just works, right? Because this is just so easy to prove that the image of a compact set is compact. Well, you just take an open covering of your image and then just pull it back, right? And then the pullback is going to be an open covering of your domain. So it's going to be an open covering of X. X is compact, therefore it has a finite subcover. Now you push it back forward, and that finite subcover is now a finite subcover of your image. It's really... so even though we might not understand why that definition works, this thing just shows you that, okay, we're on the right track. Here's another nice little one. Let's say we have a bijective continuous function from x to y. X is compact and y is Hausdorff. Then F is a homeomorphism. Okay, so how do bijective continuous functions fail to be homeomorphisms? Right, so we just got to prove that the inverse is continuous. So let's do that for closed. So if we can show that F is a closed map, then F inverse is going to be continuous. Well, if A is closed in X, right? Since X is compact, A is compact. The image of a compact set is compact, but its Hausdorff, a compact set in a Hausdorff space, is closed. So, I just think that's a nice little proof. It's just, again, it just shows you how things work. Okay, now let's get on to the real stuff, products. So what we want is, of course, that the product of compact spaces is going to be compact. So what we're going to find out is that finite products of compact spaces are going to be compact. And the way we're going to prove that is just basically by induction. So, you know, in one dimension, it's compact, and so we can get a finite subcover there, and then we go to the next dimension, and then we've got a finite cover of the sitting over the finite sub, and then you keep on going. So you've got finite times finite times finite. So you end up with finite if there's a finite product. Of course, that's not going to work for infinite products. And but the fact is that the product of compact spaces is going to be the infinite product of compact spaces is going to be compact in the product topology. So it's going to continue that same thing where the product topology is nice and it behaves kind of like finite products. That's called the Ticking Off Theorem. And it's actually one of the most important theorems in topology. And it's actually kind of hard. And so that's going to be one of the last things we're going to look at. I think it's considered one of the two most important theorems in this kind of point set topology, that and the Urison lemma, which kind of has to do with showing things, spaces unmetrizable. And again, hopefully that's where I want to end up with those two things. Again, these are a couple of Russians, Soviet topologists from the 20s and 30s who came up with this. Okay. So we need some technicalities. The first thing, technicality, is the idea of a slice. So a slice in a product space is just a set of this form. Where you, and of course, X cross Y naught is also a slice, but I'm just doing it, just worrying about this from this moment. So get a slice in a product space is that one. A tube in the product space is some basis element containing a slice. So right, so remember the basis elements in the product topology are the form U cross V, where U is open in X and V is open in Y. So W cross Y, right, well Y is the whole of that space. So W is just a neighborhood in X. Okay? And so this is an example here, like of a tube. So this black thing here is an example of a slice, and here's a neighborhood W down here, and W's cross Y. That's an example of a tube. So you can see why they call it a tube. Okay. So here's the tube lemma. So we've got a product space X cross Y, and Y is compact. If N is an open set in the product space containing a slice, then N contains some tube about that slice. And that tube is given by W, where W is a neighborhood of X naught in X. Okay. Now notice we're going to need compactness for this to work. For example, because if you look at this thing here, where is, think of R2, you think of that set there, which looks like, what does it look like? 1 over y squared plus 1 kind of looks like. Right, so that's a pretty nice open set. But the thing about it, of course, is as you go to infinity, the neck gets narrower and narrower. And so there's no neighborhood that you can, there's no tube that you can actually stick in there. So the compactness is needed for the tube to work. Okay, and the proof is not so hard. Okay, so consider the slice X cross Y. Well, this slice is homeomorphic to Y, but Y is compact. So if we, so first off, we start off with a cover of the slice, and we can have it that the cover just lying in N. right? Because if the cover lies outside of N, if we just intersect it with N, it puts it back inside N, and it's still going to be open cover. Okay? Now, since the slice is compact, and we're covering it with an open set, so notice we're using this lemma 26.1 all the time without actually saying anything, right? Because when we talk about open cover, we're not worrying about whether it's open cover in the subspace or the whole space, because it doesn't matter. Okay, so that means since this is slice is compact, that means the cover, we can assume a finite subcover. So that means we've got a whole bunch of UI, finite number of UI cross BIs that cover the slice. So for example, in this picture here, we've got something like that. So we just let our W then be the intersection of all the UIs. And again, because it's a finite cover, we're only doing a finite intersection of open sets. So it remains open. And non-empty, right? Because X naught is going to be in here. Okay, so this cover of X naught cross Y also covers W cross Y. And we have this tube then, since this cover lies inside N, the tube also is going to lie inside N. And that proves it. Okay, so this is basically doing one dimension of the two-dimensional proof. Okay, so the tube lemma then allows us to do the last thing, which is the next thing, which is the product of finitely many compact spaces is going to be compact. Okay, so we do the usual thing. So we start off with an open covering of our product space. And so we want to show that there is a finite subcover. Now, for each X in big X, the slice that's associated with X has a finite subcover from A. Okay, that's what so let N be the union of this subcover. Then by the tube lemma, we have a tube for each X. We have a tube also covered by this finite subcover. Okay, so what's the picture like? So here's X cross Y. We've taken a slice X. Since X cross Y is compact, right, because it's homeomorphic to Y, which is compact, if we've got our open cover of like this, a finite subcover of it is going to cover just this slice here. And then if we have a look at the union of that finite subcover, that's going to be an open set. And so we have some tube then around our X. Okay. But this is true for all, so for any X in X, for all the X's, we can find a little WX. So this is X1, WX2, etc. So this gives us an open cover of X by these neighborhoods, right? And the corresponding tubes, so if the neighborhoods cover X, the tubes are going to cover X cross Y. But since X is compact, we can have a finite number of neighborhoods WX, which is going to cover X. And so this is going to give us a finite number of tubes, which is going to cover X cross Y. So we've got a finite number of tubes. Each tube has a finite cover from our collection A. So we've got a finite times finite is still finite, so therefore we have a finite covering of X cross Y. And then we just proceed by induction, right? Because then, as we've noted before, X1 cross Xn is homeomorphic to X1 cross Xn minus 1. So we can just do induction to get all finite products. We're going great guns. You comfortable with all this?
Wait, so I think I missed, why is that actually a sub-collection of Subspaces? The WXIs.
So the WXs, you know, they just give the base of the tube. So we've got finite number of bases of tubes. That means we've got finite tubes. So we've taken our space X cross Y. And so we've found there's a finite number of bases of our tubes. So that gives us a finite number of tubes, which cover X cross Y. And for each tube, now we go back to A, because we've already shown that for each tube, there's a finite number of elements of A which cover the tube. So we've got a, so for example, if N is the most that's needed to cover a tube, and we've got M tubes, then we've got at most N times M elements of A. So I already mentioned that infinitely product of compact spaces in the product topology, the Ticking Off Theorem. Oh, so the last thing, have we run out of time?
1 minute.
Okay, so the finite intersection property is just the closed set version of the open set definition of compactness. So the finite intersection property means that if, so a collection has the finite intersection property if for every finite subcollection of sets of that, the intersection is non-empty. So the classic example, what you've got that is when you've got a nested series of subsets. So then any finite collection of it is going to contain the bottom subset, and so it's going to be non-empty. And so the alternate definition of compactness is X is compact if and only every collection of closed sets having the finite intersection property, the intersection of all the closed sets is non-empty. So again, it's a non-intuitive thing, but it turns out to be super useful. So for example, this is how we're going to end up proving Ticking Off's theorem, and you can use it to prove the uncountability of the reals, etc. So it's a useful thing. And so that's where we'll finish up on Friday. Okie doke.
That's when we never did that in the cardinality chapter, because we could just get it for free along the way, basically.
But so you never.
Well, we did in foundations, but we never proved the uncountability of the reals.
Oh.
Here when we talked about cardinality, right? So is that just because we're going to get it for free as we pass by here?
Yes, when we talk about, so in the next section when we talk about the reals, compact sets of the reals.